Alrighty, well, hello and welcome to our our first class after Labor Day. I hope your Labor Day was totally solid. Mine was, but now we're back to it. Couple of announcements before we get moving. So the first thing I wanted to no thank you. There we go. The first thing that I wanted to bring to everybody's attention, which hopefully you've seen my most recent posts. But our first electronic lab is done. It is currently live on my lab section's Canvas. And if it's not already live on yours, it should be coming to you soon. If it isn't, contact your lab instructor because they're the only ones with jurisdiction over your lab Canvas. So it's live for me. If it's not live for you, it should be coming soon. And you should see. Whoops. If you haven't, you should check out the Canvas post. Oh wait, hang on. I'm like, look at the Canvas post. That post was only to my section. So if you're in my section, I posted all about it. I'm sure the other lab instructors have done similar things. But the one thing that I did want to point out about eLab, the electronic lab, there's a kind of pre-lab section for you to read, and there's also links for videos for you to watch so you can familiarize yourself with kind of the tools and techniques that are used. But tonight, in office hours, I'm gonna do a mini lab lecture. I'm gonna be talking about the content of the lab, some of the background information, some tips to watch out for. So if you are someone who maybe is looking for a little more explanation, maybe not so much reading on your own, this would be a great place to start because I'm going to walk through. You're going to have a chance to answer or ask questions. I'll be answering them. Maybe I'll ask you questions, and then you can give me satisfying answers. So check that out tonight or later. It'll be the 9/9 lab live stream. I'll be doing a mini lab lecture, and then it'll be normal office hours as usual. So that's one piece of information. Second piece of information. So for those of you who have not read my post, I want to make sure that everybody knows. In the syllabus, it originally said that I'd be posting lecture assignments through Canvas and they would be graded. I have canceled this. Mostly because I've been working on converting the lab exercises to Canvas quizzes, and these things are stinking long. And as I was doing this, I was just like, dudes, these students do not need more problems to have to complete for points. These exercises are scary long as it is, and so I didn't want to heap more on top of it. So there will not be graded lecture homework. There is lecture homework assigned out of the book for practice for your benefit, if should you want it, and that's available under files. But there will be no formal homework assignments that you'll have to worry about due dates, etc. That being said, I highly encourage everyone to check out the lab exercise 2 assignment. It just got finished. It just went live on my lab Canvas page. It should be coming soon, to yours, to a lab Canvas page near you if it hasn't already. And it is a 2-question, 2 questions, 2 answers. 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 2 questions, 2 And this thing is on nomenclature, which is naming. It's all the stuff we've been talking about in lecture. And I recommend you get a jump on this thing as fast as possible because it is long. Lab exercise 2 has over 140 problems. All right. Now, these things are not like insane word problems. It's literally 2 types of things. It's here's a compound, chemical formula, what's the name, multiple choice, or here's the name, what's the chemical formula, multiple choice. All right. And so it's not that they're long, but this thing does take a lot of time. So if you look at the due date and you're like, I'm not going to start that till whenever it's due, you may not be able to finish it. So I would definitely recommend getting a jump on it. Again, if you're in my lab section, it is live. If you are not in my lab section, then it either it's live already or it will be becoming available quite soon. All right. So with that being said, those are kind of our pieces of business before we get started. Let's continue on with chapter 3. Now, you now know how to handle all of ionic nomenclature. You can name any ionic compound I can throw at you, or at least theoretically. If you want practice with this, hit up lab exercise 2 because it's nothing but nomenclature. All right. And as of right now, you can do all the ionic problems. We still need to talk about covalent nomenclature. Covalent nomenclature. All right. Now, with covalent nomenclature, it's a little bit different than ionic nomenclature. For example, with the ionic compound, how about KBr? All right. We know that you name this thing with the cation name, which is potassium, followed by the anion name, which is bromide, right? And you gotta sneak in that IDE ending. Now, the reason why we can get away with just saying the cation name followed by the anion name is we know from the periodic table that potassium is always +1 and bromide is always -1. So these 2 ions will always have a 1-to-1 ratio, all right? Because their charges are the same. So we don't ever need to worry about K2Br. That'll never exist. It'll always be KBr, 1 and 1. With covalent compounds, it's not that cut and dry. For example, you could have a compound that is CH4. Another compound made of carbon and hydrogen is C2H4. All right? We can't just call this cannot be carbon hydride. It can't be carbon hydride because then how do you tell it apart from this? Right? The trick with covalent compounds, ionic compounds are simple. It's always the same ratio of elements. Covalent compounds, there are no fixed ratios. It could be, oh, wow, sorry. It's loud. It could be CH4, it could be C2H4, it could be C2H6. There's all sorts of different ratios that they can come in. So we need a different system of nomenclature in order to name these covalent compounds. All right. Now, a little bit of a definition. A little bit of a definition. That hardly makes sense. Covalent compounds have all non-metal elements. All right, so they're just non-metal elements. That's how you know you're dealing with a covalent compound. If you got a metal up in there, then you know you're ionic. If you're all non-metals, you're dealing with covalent compounds. And the way you name covalent compounds you use a series of prefixes. All right, you use prefixes to specify the exact number of elements of each element present in the compound. All right, now mono means there's one. Di means there's two. Tri means three. Tetra, that might be a new one to you, is four. Penta is six. So, no, it is not. Penta is five. Hexa is six. Hepta is seven. Octa is eight. Nona is 9, and deca is 10. All right? These are the prefixes that you use to explicitly enumerate how many elements of each type are present in your compound. So, for example, if you were asked to name the compound C2H4, this would be dicarbon, all right, because we got two, tetrahydride. Again, because we have two carbons, you give the prefix di. Because we have four hydrogens, you give the prefix tetra. And you'll notice that we're still hanging on to that "ide." Whatever element comes last gets that IDE ending that we're familiar with from ionic nomenclature. C2H6 would be dicarbon hexahydride. Right? C3H8 would be tricarbon octahydride. And again, whatever prefix, however many, whatever your atom count of that particular element is, whatever that atom count is, you use the corresponding prefix to explicitly state how many of that element are present. All right? So it's fairly easy to move from the chemical formula to the name. It is just as easy to move from the name to the chemical formula. So for example, if I asked you to write the chemical formula out for Kyle, that is a great question. Does capitalization matter? That is an excellent question. So, so chemical names are not proper nouns. Which means they should only be capitalized at the beginning. Oops. Um, Chemical names are not proper nouns, which means they should only be capitalized at the beginning of the sentence. That being said, I'm not really going to test for that. At least here, when it comes to lab reports, when you're writing lab reports, which we will be doing later on in the semester, if you have carbon dioxide in the middle of a sentence in your lab report, it should not be capitalized. But it won't really affect kind of the testing environment here. When you're doing formal scientific writing, you'll need to keep that in mind, but you don't have to worry about me testing you on an exam on rules for capitalizing or not capitalizing. But the thing to remember is they're not proper nouns, is the technical answer. All right, let's name a few of these, starting from the chemical formula. And we could name and maybe there we go. All right, so the first one, if we're naming the first one, we've got two silicons, right? We've got two silicons, so this will be disilicon. We've got four oxygens, so this will be Now instead of you don't say tetraoxide, you say tetroxide. All right, so there's disilicon, tetroxide. If we look at our next example, we have four phosphoruses, so this would be tetraphosphorus. And then we've got 10, so it'll be decoxide. All right, and finally, looking at C3H4, this would be carbon tetrahydride. All right, so really with covalent nomenclature, it just comes down to knowing the prefixes. Once you know them, it's simple to move back and forth from the formula to the name, from the name to the formula, because each is just giving you a laundry list of elements. It's telling you how many things you need of each different type of thing. There's one there's one kind of idiosyncratic rule that you've got to keep an eye out for, and that is this. When you have one of the first element in a compound, you do not include the prefix mono. Oops, or mom. do not include the prefix mono for that element. All right. Now you may be going, oh man, I knew that there would be like something would show up to mess this thing up. It was too straightforward. It was too easy. Now I've got to keep track of like this thing, right? Let me give you a piece of good news. You actually already know this rule. Yes, you already know this rule. Everybody at home, can you tell me what this compound is? The name of this compound? Hopefully a chorus of carbon dioxides. Exploded in rooms around Sacramento and El Dorado and Placer counties, wherever we're coming from. I don't know why I put it in plural, though. Carbon dioxide is the name of this compound. And you knew that. Even though we only have one carbon in this molecule, you did not name this monocarbon dioxide. It's just carbon dioxide. Let me hopefully drive this point home. Someone please tell me the name of this compound. Well, as you already know, this is, whoa, not cabin. This is carbon monoxide. All right. You already intuitively knew that you do not include the mono. Yeah, BMP draws, you got it. You do not include the mono for the first element, carbon, but you do use the prefix mono for the second one, if there's only one. All right, so that's just the one wrinkle to keep in mind. If there's only one of the first element, it does not take the prefix mono. If there's one of the second element, it totally does. But fortunately, this kind of weird naming idiosyncrasy, you already know. All right? Okay. Now, that is covalent nomenclature. You can now name all ionic compounds and covalent compounds. So there's one last bit of naming out there, and that is acid nomenclature, how to name acids. And I'm not going to cover that situation until we get to acid. So in chapter 4, we'll learn about acid-base chemistry, and I am planning on covering acid nomenclature when we reach that point. So for now, you don't need to worry about it. We'll be picking that up a bit later. All right. So at this moment in time now, you can handle any nomenclature problem that can be thrown at you, and there's over 140 waiting for you in exercise 2. So I would get cracking on that. All right, now so now our next topic in chapter 3, moving right along, is something called we're gonna look at the mass percent, or the percent mass of an element. All right, percent mass of an element in a compound. Actually, gonna scoot this up here. All the fun things I could never do on a traditional whiteboard. Percent mass of an element in a compound. All right, so the the percent mass, so this has an equation, of an element is equal to the mass of that element divided by the total mass of the compound times 100. All right, this is the equation for the percent mass of an element, and let's go ahead and apply it to the following example. All right, let's calculate the percent mass of each element in the molecule CHCl3, otherwise known as chloroform. All right, let's calculate the percent mass for each element. Starting with carbon, let's go ahead and give carbon first go. So this will be equal to the percent mass of carbon is equal to the mass of carbon. Now here we got to look up carbon's mass on the periodic table, and carbon has a mass of 12.01 AMU, and now we have to divide it by the total mass of the compound. Now here we have to add up all of the individual atomic masses. So carbon has a mass of 12.01, hydrogen 1.008, chlorine has an atomic mass of 35.45, but you got to remember that we're dealing with three of them, so we actually got to multiply that 35.45 by 3. All right, so 35.45 times 3 plus 1.008 plus 12.01 comes out to be 119.368. One thing you'll notice, if you apply the rules for sig figs for the numbers that I've used, our least precise number is precise to the hundredths place, so we need to round to the hundredths place. I'm going to wait to round to the end, but I'm putting this mark there so I know that this mass has 1, 2, 3, 4, 5 sig figs in it. This is 119.368 AMU, and this is our last significant digit. All right, and now we, oops, hang on. So 119.368 AMU, but our last significant digit is in that second decimal place. And those lines are there to remind me. Now we multiply this by 100, and this will give us our mass percent of carbon. So we have 12.01 divided by 119.368 times 100, and our answer is long 10.0613. The number keeps going, but we don't need to because of sig figs. Our denominator has 3, but you'll notice our numerator has 4. So 1, 2, 3, 4. This one will round down, and our mass percent of carbon will be 10.0613. 0.06%. All right. That's our mass percent of carbon. Let's look at our mass percent of hydrogen in this molecule. All right. We have a percent. I don't know what accent that is. A percent mass of hydrogen is, so our atomic mass of hydrogen is 1.008 AMU over our molecular mass, which we previously calculated. We get to reuse it, which is nice. And again, this denominator has 1, 2, 3, 4, 5 sig figs. Multiply this by 100. So we have 1.008 divided by 119.368 times 100. So our value is 0.84444474. It keeps going, but we do not have to. Our numerator is 4 sig figs, our denominator has 5, so we are limited to 1, 2, 3, 4. This 4 will round down, and so our percent mass of hydrogen will be 0.8444%. All right, now finally, let's take a look at chlorine. All right, now here's the one thing to keep in mind. So percent mass of chlorine. Now here, we know that chlorine has a mass of 35.45 AMU, but we have 3 chlorine atoms. So it's not just 35.45 AMU, it's 35.45 plus 35.45 plus 35.45. You have to add all of these together. So our numerator here is going to be 106.35 AMU. All right. One thing you'll notice, so here our denominator has 5 sig figs, and our numerator also has 5 sig figs. So this percentage will actually be more precise than the others, or it'll have more significant figures than the others. 106.35 divided by 119.368 times 100 is 86.094229. It keeps going. We do not have to. We get to keep 5 sig figs. 1, 2, 3, 4, 5. 2 will round down. So this will be, oh, sorry, that's not 86. That should be 89. So this will be 89.094%. All right, so those are our mass percents of each element in the molecule of chloroform. Okay, question, Bailey, let's see. What if we started with 1.01 as hydrogen's mass? Yep, because your periodic table is more simplified. Okay, here's the thing. Bailey, that is an excellent question. So what would happen if you did 1.01? So Okay, so here's the thing. Um, so this really comes down to, so when do you risk the potential for losing significant figures? And it's usually in not usually, it's like in a testing context, right? Um, when I'm writing the problems, I craft them in such a way that it shouldn't make a difference. And by that, I mean one of two things. So one, I wouldn't, if I were doing a percent mass of each element, I wouldn't pick one with hydrogen. I'd pick one where no matter what periodic table you're using, you would have at least 4 sig figs in it. And it would be multiple choice, so you'd be able to figure out which one is correct by the values given. If I were to ask you to calculate a numerical answer, I would provide the specific AMUs for you to use within the problem. So if it's multiple choice, you'll be able to tell because you're like, well, according to my calculation, I'm getting, or here, let me see. If you used 1.01, I'm just curious to see what the number would come out to be. 119.368. So Bailey, using that value for hydrogen, you would get 0.846%. All right, and if you calculated 0.846, but your available answers are 0.8444 or 0.973 or 1.24, and you had to pick on a multiple choice situation, the sig figs may be different or may look wrong according to your calculations, but you got to select one right answer. It's not going to be the 0.91, it's not going to be the 1.21, it's going to be the 0.84, even if the sig figs don't match what you have going on. If I'm going to do a numerical entry problem, like, okay, here, punch in the exact number with the correct number of sig figs, in that problem, I'll explicitly state use these values for the AMU of each element so that everybody's going off the same thing so everybody can get to the same answer. Does that make sense? Hopefully that answers your question. Whoops. Oh my goodness. So that's how that's going to shake out in a testing context. Either you have to use logic to figure out which of these multiple choice answers looks the most correct, even if your sig figs are different because you're using a different periodic table, for example, or for numerical entry, I'll provide you the AMUs explicitly so that you'll know that you're using the value that will get you to the correct number of sig figs. Totally. Okay, awesome. And that was an excellent question to raise because it's one that's particular to this kind of online distance learning thing experiment that we're all engaged in. And there's some weird quirks that are slightly different than normal in a normal semester. I'd provide you with the periodic table, so you wouldn't have to worry about it. I'd say, well, just use the periodic table I give you, because that's what I'm using for the calculations. But things are a little more fluid. Fluid now. Okay, let's see. All right. So that's our first example. This is a fairly straightforward example, calculating the percent mass of each element in a compound. But this is not the only way this type of problem can come into play. All right, there are other types, more complicated examples, like the one we're about to do. So let's crack into this problem, which is a bit next level. All right, so in this example, I tell you that the mass percent of chlorine in the molecule CF2Cl2 is 56.64%. All right. If if there is 5.21 grams of chlorine in a sample of CF2Cl2, how many molecules of CF2Cl2 are in that sample? Question mark. All right. Now, before we dive into this problem, Andrew just asked an excellent question about sig figs. We're going to answer his question, then we'll circle back and solve this. So Andrew said, so in the previous problem, we had 3 chlorines, right? I should write a children's book, The 3 Little Chlorines. So, Andrew's question, if we had multiplied the mass for chlorine by 3, we would only have 4 sig figs. Now, here's the thing. So your question is, do we have to always add elements mass, or at least apply the sig figs rules for addition? And Andrew, that is an excellent question. And the answer is... in this instance, the answer is yes, and here's why. When you have a molecule... So our total mass of chlorine the value here is 3 times 35.45 AMU. All right, but this 3 that we're multiplying comes from this guy right here, and this is not measured. That is an exact value right there. There are exactly 3 chlorines, and so what the act of multiplying an exact quantity is it's literally saying sum this 3 times. So the rules for multiplication that we developed for sig figs are when you're multiplying 2 numbers that are measured quantities together. But because this number has no sig figs, what you're actually doing is you're adding this 3 times together. Each one of these has its final significant digit in the tenths place. So when you multiply this through and you get your answer, or add them all together, 106.35, your answer must have its last significant digit in the same place as the least precise number, and they all share precision. So when you are multiplying a non-measured quantity by a measured quantity, what you're doing is addition. You're just adding it together that many times, and therefore your answer's precision must reflect the precision of that measured quantity. All right, and that's why the last sig fig here is in the same place as the last sig fig here. All right, excellent question, Andrew, and you're picking up on kind of the more nuanced. Okay, you're so totally welcome, and here's the good news: you're picking up on like the more nuanced kind of questions with sig figs, which if you're catching something that is that kind of specific and erudite, it means that you have a good grasp on the rules as a whole. So I would definitely feel encouraged about how you're doing. Okay. I wanted to, so let's get back to the other problem. I wanted to stop and answer this question fully because it is an excellent question. It's an excellent question that deserves taking our time. All right, but now we can move forward to this weird problem. All right, I'm going to go ahead and read it again. The percent mass of chlorine in the molecule CF2Cl2 is 56.64%. If there is 5.21 grams of chlorine in a sample of CF2Cl2, how many molecules of CF2Cl2 are in that sample? Okay, if when I read this the first time or read it again just now, if you felt your anxiety spike because you have never seen a problem like this before and you have no idea how to solve it, that's good. The reason why that's good is you will feel that feeling again when you take my exams. I guarantee you there will be problems on the test that that you've never seen before. You will not have been able, you won't have seen examples in the homework. You won't have seen me do examples like them in lecture. There's going to be problem types that are totally alien. That means what I'm actually testing for is not your ability to memorize how I do a problem and then do it. I'm testing for your ability to problem solve, all right? That, when you think about it, is the one thing that medical schools want you to take out of general chemistry anyway. They're not very concerned with, do you know what a mole is? Do you know how to convert from grams to moles? They're far more interested in, did you learn how to assess a situation, make a diagnosis, and carry it through? That's what they are looking for. So that's what this class has to test for. That's the service I have to provide. So this is a test simulation. This is an exam simulation. The first thing you do when you feel overwhelmed by a new problem is take a deep breath. All right? Take a deep breath and start by identifying what you're trying to find. Oops. That is step number one, always. What are we trying to find in this problem? All right. And what we're trying to find is laced in right here, right? How many molecules? We're looking for our molecules of CF2Cl2. That's what we're going for. Once you've identified what you're trying to find, you need to list out what you've been given. All right? Because there's information in every problem that will lead you to the answer if you can assemble it. All right? First, we know we've been given that the percent mass of chlorine in this molecule is 56.64%. All right? It's laced in right up here. 56.64%. This is huge, all right? This is critical because percent mass has an equation associated with it, all right? And every time you're given a quantity that has an equation associated with it, you need to write out that equation in your given information, because more likely than not, that algebraic expression will be a roadmap to solving this problem. So let's write the equation for mass percent of chlorine. Mass percent of chlorine is equal to the mass of chlorine in the molecule over the total mass of CF2Cl2 times 100. All right? That is another critical piece of given information. Now, are there other things we've been given? There is actually. There's one last thing, and that is right here. We're actually given the mass of chlorine. We're told that the mass of chlorine in the sample is 5.21 grams. All right? Now, let's go back to our equation for mass percent and look at what we have. We know the percent mass of chlorine because we were given it right here. We also know the mass of chlorine. That means that this equation allows us to solve for the total mass of CF2Cl2. Right? That's what this equation gives us. Question. Is that what we're after? No, we want molecules. We want molecules, and all we can solve for are grams. But let me ask you, have you ever been given a problem this semester where you're given a mass of something and you're asked to convert it to molecules of another thing? The answer is totally. We can take a mass and convert that mass to moles. And then we can take our moles and convert them to molecules. That is something that we've done over and over. It's something we've been doing since the first chapter we ever covered, which was chapter 2. So we know how to do this process. This problem is actually the same one we've been doing. It's just been dressed up in a costume. It's been disguised as a percent mass problem when really it is just a it's been disguised as a percent mass problem when really it's just a convert this mass, how many molecules are there in a total mass of a sample. All right, so that is our roadmap. Let's execute this plan. All right, let's start doing some algebra. So we're going to start with our percent mass of chlorine is equal to the mass of chlorine over the mass of CF2Cl2 times 100. All right. Now, we want to, just as a quick note, we want to solve. If we're going to solve for this, for our mass of CF2Cl2, we got to get it out of the denominator, right? We got to jailbreak it from that denominator. So we need to start by multiplying both sides of this equation by our mass of CF2Cl2. All right, it'll cancel this denominator, giving us an equation that has the mass that we're after times the percent mass of chlorine is equal to the actual mass of chlorine times 100. All right. Now, because we're solving for our mass of CF2Cl2, we need to isolate it on one side of the equation. So we need to divide both sides by the percent mass of chlorine. So we get a new expression that'll allow us to solve for the mass of CF2Cl2. It's equal to the mass of chlorine times 100 divided by the percent mass of chlorine. And we know what both of these are because we were given them in our original problem. So we can plug in our numbers and calculate our mass of CF2Cl2. So our mass of chlorine is 5.21 grams of chlorine. So 5.21 grams times 100 divided by the percent mass of chlorine, which is 56.64. All right, let's crunch our numbers. 5.21 times 100 divided by 56.64 gives us a value of 9.19844 grams. Sig figs wise, we can only keep 3 because our mass only has 3. I am going to wait to round till the end because this is not the final answer, right? You got to save your rounding to the end, but we do need to keep track of how many sig figs we have, so I put 3 lines into this value to remind myself that I have 3 sig figs. All right, let's convert our grams to moles. So we have 9.19844. 3 sig figs here. This is grams of CF2, Cl2. If we're going to find molecules, our first step is we have to take our grams and convert them to moles. All right, which means we have a molecular weight to calculate. Carbon has an atomic mass of 12.01, fluorine 19.00, chlorine 35.45, but we have 2 of each, fluorine and chlorine, so we got to remember to multiply those dudes. It's 35.45 is 70.9 plus 70 plus 12.01 gives us a mass of 120.91, and you'll notice this number has its last sig fig in the hundredths place, as do all of our decimals, so that is the value with the correct number of sig figs. That we'll be rolling with. Grams cancel grams, leaving us with moles. Now we have one more unit conversion in the cards. We need to convert from moles of CF2Cl2 to molecules. And 1 mole has 6.022 times 10 to the 23rd molecules. Now moles here cancel. And now we're ready to crunch our numbers. So we have 9.19844 divided by 120.91 times 6.022 times 10 to the 23rd. Our value, my value here is coming out to be 4.581342 times 10 to the 22nd. We can only keep 3 sig figs, however, and this one will round down. So our final answer, correct value with the correct sig figs will be 4.58 times 10 to the 22nd. The correct units here are molecules of CF2Cl2. And that is our final answer. All right. So that is another example of how percent mass can be incorporated into a problem, touching on concepts that we've already learned. All right. Now, we're going to move on to, let's see. It is entirely possible. Let me take a look, because that actually would drastically affect my final answer. So let me double check my molecular weight. Oh, okay. I'm good. Okay. Solid. Okay. So the last thing we're going to talk about today, and this is the second to last topic in chapter 3, is we're going to dig into empirical formula. All right, empirical formula. Now, the thing to remember is, and I know we introduced empirical formula at the start of this chapter, but it's been a minute, so I'm just going to refresh our memories. The empirical formula for a molecule depicts the simplest whole number ratio between elements in a compound. All right, simplest whole number ratio between elements in a compound. Now, the way that empirical formulas are determined are through something called elemental analysis, where you take a compound and there's this instrument that will atomize it, that'll break it down into its constituent atoms, and you can determine what the mass of each element in the sample is. So, for example, or consider the following example. Elemental analysis of a sample of an unknown compound reveal that it contained 1.651 grams of silver and 0.1224 grams of oxygen. Determine the empirical formula for this compound. All right. Now, here's the method. All right. Here's the thing to keep in mind. When you look at a molecular equation, for example, in a molecule of water, H2O, we know from the chemical formula the ratio between hydrogen and oxygen, right? The ratio of hydrogen to oxygen is 2 to 1. Now, this is not a mass ratio. This is a molar ratio. This is 2 moles of H to every 1 mole of oxygen. All right? So, the first thing you've got to do when you're solving this problem is, here, hang on, I need to open a new layer. The first thing that you've got to do when you're solving this problem is determine the moles of each atom. All right, determine the moles of each atom. So let's do that. We've got 1.651 grams of silver. And we need to convert from grams to moles. So we put grams of silver in the denominator. You put moles of silver in the numerator, and where we go, there it is. Silver has a mass of 107.87 grams per mole. So grams of silver cancels. Oops. So we take 1.651 divided by 107.87. This comes out to be 0.01531 moles of silver. And next we do the same thing for a mass of oxygen, 0.1224 grams of oxygen we need to convert to moles. So we put grams in the denominator, moles in the numerator. And 1 mole of oxygen has a mass of 16.00 grams. Grams of oxygen cancel. Take 0.1224 divided by 16 is 0.007650 moles of oxygen. All right, that's step number 1. Take your masses, determine the moles of each atom. And the reason why we're doing this is we want to find the empirical formula for this compound with silver and oxygen in it, right? The empirical formula will have some subscript for silver, I'm going to call it X, and some subscript for oxygen, I'm going to call it Y, all right? The subscript for silver are the moles of silver. The subscript for oxygen are the moles of oxygen. So once you have determined the moles of each atom, you want to plug the moles into the chemical formula. All right, that is your step 2. You determine the moles of each atom, and then you plug it into your chemical formula. All right, so we're going to take actually, I need to open a new slide for that. So we're going to take these two values and plug them in. We're going to have silver with a subscript of 0.01531, and we're going to have oxygen with a subscript of 0.007650. All right, step number 3. Oops. Step number 3 for determining the empirical formula, after you plug in your moles to the formula, is simplify. Simplify the ratio. The empirical formula, as I stated at the beginning of this problem, is the simplest whole number ratio between elements in a compound. And even though we do have that ratio here, and this is the correct ratio that we're dealing with right here, the correct ratio is 0.01531 to 0.007650. That ratio is accurate, but it's not the simplest, right? In an empirical formula, you need the simplest whole number ratio. So we need to excuse me, I got the hiccups really bad all of a sudden. We need to determine what that simplest whole number ratio is. And the way you simplify is take each subscript in your empirical formula and divide by the smaller of the two. Here's why. When you divide by the smaller of the two, instantly that element's subscript is just going to become 1. All right? Oxygens will simplify straight down to 1. Silvers, well, let's see what happens. 0.01531 divided by 0.007650. All right, now you'll notice silvers doesn't get instantly better. Just oxygens did. Silvers doesn't. Silver subscript is now 2.0013. Then it keeps going. So this is not This is not a simple whole number ratio yet. All right, the fourth and final step is you need to evaluate the decimals. That remain. All right, and here's what I mean by that. So the number 2.0013 is not a simple whole number ratio, but 2.0013 is approximately just 2. All right, that decimal is small and it's close enough to actually just being 2 to where we can ignore it. We can round it down and just drop all the decimals, treat it as an integer. Because at the end of the day, your empirical formula needs to be a simple whole number ratio, but also at the end of the day, no data set is perfect, right? Data is flawed. There's errors that are made in collecting it. There's errors that people who are carrying out the elemental analysis may make. There's limitations to the scales of measurement, etc. So your numbers are never going to come out when you do this in the real world. Your numbers will never come out pristine. When you divide by the smaller of your two numbers in your ratio, the smaller one will always be 1, but the other one isn't ever going to be 2 on the nose, all right? It'll be like it was here, 2.0013, or maybe it'll be 1.99846, right? Something that's close enough to where, or if it's close like that to an integer value, you can round it, and it'll come out to be 2, all right? Now, I am looking at the time, and there's one last thing I need to mention about this fourth and final step. Whoops. Four is evaluate. The decimals. That remain. All right. Let's say you're doing a problem. Let's say we've got carbon and hydrogen, and let's say that we have just done step 3 and now we're on step 4, and we have 1 carbon and we have 1.5 hydrogen. How do you handle that decimal? All right, well, you can't round it. You can only round if it's really, really close to an integer. This is not. It's somewhere in the middle. All right, so you have to ask yourself, what's 1.5 as a fraction? Well, as a fraction, 1.5 is 1 and 1/2. What's that as an improper fraction? Well, that would be 3/2. All right. What you do is you rewrite this as that improper fraction, C1H3/2, and then you multiply your ratio by that denominator. All right, so the empirical formula here is C2H3, all right? When you're dealing with decimals, you have to ask yourself, you can't just round automatically. You can only round if you're very, very close to an integer. You have to ask yourself, what fraction does this decimal represent? And here are the types that you will see in the future on empirical formula problems that you'll need to work on and evaluate. So decimals to fractions. All right, you may very well see the following decimals and have to turn them into improper fractions in order to finish the empirical formula problem. So if you have 0.25 for your decimal, this as a fraction is 1/4. 0.33, the decimal, as a fraction is 1/3. 0.5, we have already talked about that, as a fraction is 1/2. 0.67 as a fraction is 2/3. And finally 0.75 as a fraction is 3/4. All right, so these are the ones that you should be on the lookout for if you have a fraction that is close, or a decimal that is close to one of these. Do not simply round. You need to convert it to a fraction and use the method I just showed you to get those that integer number. All right, you could run into any of these on the test. I will probably on exam 1 put all of them. You might see one of them. All right, and again, you're not going to see, for example, you're not going to see exactly a number that's exactly 1 point, or a number that's 2.75 exactly. You might see a number that's 2.74883, and you'll have to identify and go, wait a minute, this is 2.75. Let me convert this to a mixed number and then an improper fraction, and let me finish this empirical formula problem. All right, we are we're a few minutes over. This is where I'm going to close our lecture. If you're feeling a little intimidated or worried about this whole deal, don't be. We're not done talking about empirical formulas. We're going to come back and open up Monday's lecture with a couple more information, with more information, a couple more examples. We're going to grind through this together so it becomes more familiar, all right? In the meantime, I totally encourage you to check out the empirical formula problems in the back of the book. In the back of chapter 3, I've assigned some. So totally hit those situations up. And yeah. Okay, Murat, great question about the decimals. Yeah, okay, so here's the deal. For, yes, totally, for Emma, for Murat, and the rest of the class that's wondering this. Here. So even though all those decimals, the proper way to handle them would be to do that sort of thing. Exactly what you're doing. I will only test you on... So Murat, your handling of it is spot on. I'm only going to test you on 0.75, 0.67, oops, 0.5, 0.33, and 0.25. So your treatment is spot on. I'm only going to give you fractions that are, or decimals that are near these numbers. So you don't have to worry about things getting more exotic. Also, another question that comes up commonly, is, well, what happens if we get a decimal that's exactly between one of these? I would never do that to you. I will never do that to you. So if you do get a decimal that's exactly between 0.5 and 0.33, that tells you, because I'd never give that to you, that tells you that there's a mistake somewhere else in the calculations. Of course. Thanks everybody for hanging out. I'll see some of you tonight in our online office hours. Again, if you can't make it, email your questions in, and I can answer them remotely. Well, all of it's getting answered remotely, I guess. Anyways, have a good rest of your afternoon. I will catch some of you tonight. And this is our last lecture for the week because Labor Day is awesome. So